So hi again. We stopped when we got to the bottom of the first column because we had already gone on for quite some time. I know the schedule's going to be different this week because of the testing, so we'll just have to be flexible on how we use these videos because I think I probably will not be able to come this week. So remember, it's that I'm caring for you, all right? I'm not ignoring the fact that my primary profession is dealing with you guys and your learning. All right, so if we go over here to these questions, let's just see what we did so far. What does the electronegativity concept mean that was proposed by Linus Pauling? And it means attraction to a pair of electrons. The stronger the attraction, the higher the electronegativity, right? All right, so the higher the electronegativity, the higher the En, then the stronger is the attraction for the pair of electrons. All right. So that's we were figuring out yesterday. What does the electronegativity score tell us about an element's bonding? Well, it's related to that definition. So bonding occurs when there's a strong attraction between two elements, right? All right, and that's what we've seen when we did the Lewis dots. We saw that they came together, and that's exactly what bonding is for and does. So that's why the electronegativity score tells us so much. The third one, what elements have the highest electronegativity score and which the lowest? We saw that the highest are the nonmetals and that fluorine is the champion. And we saw that the lowest was cesium, which is the lowest one on the alkali metal column, and it is the very lowest. And when two elements combine, how do we use their electronegativity scores to figure something out? Remember, we figured out the difference in their electronegativity values. The difference in their electronegativity scores. So the fifth one, what does the polarity of a bond mean? Why does polarity of an element in a bond matter? And what is a partial charge in a covalent bond? And what's the symbol? So that's what we're going to be talking about in today's video. So let's go down to this chart. All right, so let's start this whole polarity thing with what are partial charges, because they're not whole ion charges like with ions, you know, where they have 1, 2, 3 plus or 1, 2, 3 negative. Partial means they're fractional, that is less than 1, all right? I think this is a very cool topic, and it explains an unbelievable amount of chemistry, especially physiological chemistry. So I think you might enjoy this, all right? So let's show the polarity of covalent bonds. And what we do is use this lowercase delta sign. So if you use the symbol, instead I use Comic Sans, but if you use the symbol one and put a lowercase d, you will end up with this symbol. So use the symbol font and type a lowercase d, and that will come in. All right. So in nitrogen, if you recall, this was 3.0 and this was 2.1. All right. Let me make this really big. So the partial charges, we look at those electronegativity ones, and we can see that nitrogen is much better at pulling the electron pair. All right, and remember, this is the electron pair right here. All right, this is our little pea pod, the covalent bond. All right. Well, nitrogen attracts the electrons more than the hydrogens. So because it attracts electrons more, it's given a partial negative sign. So notice I make it kind of like a shallow S, but then it has a loopy tail. At a lower electronegativity level, this means that this is partially positive. So it's not an ion. These are not ions because they don't have whole number charges, right? Partial. They're partials. Partial charges. All right, so go practice making that little sign. All right, and let me show you what this would actually mean. All right, so we have nitrogen here and we have hydrogen here. Well, because nitrogen is the more electronegative, I'll put them, I wanted a different color. The two electrons would be closer to nitrogen than they would to hydrogen. See how they are? I'm going to erase these and try again. I didn't realize this was going to be such a big point. So I can change the size of that as well. All right, let's make that more like that. All right, let me try again. All right, so I have nitrogen and hydrogen, and we're going to have the electrons between them. So what does that mean? Well, it means that because nitrogen is more attracted to the pair of electrons, that the bond is going to be closer to the nitrogen than it is. This is unequal sharing, isn't it? Unequal sharing. All right. So when we have a partial positive and a partial negative, it means that the negative one is pulling the pair of electrons closer to it. So that's why it becomes partially negative. All right. When the electrons move farther away from hydrogen, it becomes partially positive. All right. Partially positive when the electrons are farther away from it. Okay, so that's the concept. We still have two atoms. They aren't ions, but there's unequal sharing because nitrogen pulls harder on the electron pairs. And that's why? Because it has a higher electronegativity. So you can see the complexity of the situation and how Pauling, after he built this table, which must have taken him a long time, it explains so many things about the bonds in a molecule. So right now we're looking at the individual bonds within a molecule. All right, later on we'll look at what does a molecule look like when it's made of many covalent bonds. All right, now let's look at oxygen and hydrogen. We know that oxygen, do you remember, had a 3.5. It's the second highest next to fluorine, literally, in the periodic table. And then this one is 2.1. Well, then that means this, that oxygen and hydrogen, we are going to find that those electrons are going to be very close to oxygen. So doesn't that mean that oxygen will take on the partial negative sign because the electrons, which are negative, are closer to it, and that once again hydrogen has to be partially positive? All right, So what's more, unequal sharing, we found the difference is 1.4, right? Yeah, so we call this a very polar bond because those differences, 3.5 and 2.1. So polar bond means unequal sharing of the electron pair. Unequal sharing of the electron pair. Now, this is a pretty complex concept of the electron pair, meaning 2, right? So what I was saying is, even though this is complex and technical, because we'll spend time figuring it out, you will learn it and be able to use it. All right, so we have found 2 polar bonds. So this is polar because there was a large electronegativity difference, partially positive, partially negative, and this was also polar, a large electronegativity difference. So we would call it a polar bond. All right? And since molecules have many covalent bonds, we saw it can have some polar bonds and then some bonds that aren't so polar. Well, let's look at CH, carbon and hydrogen. We know this one is 2.1. And we know this one is 2.5. So after a while, you just kind of know these from using them. All right, now the difference here is very slight, isn't it? So we could say not polar here. There's some polarity, but it's not a big deal. So what would that mean if we drew it? It means if we have a carbon here and a hydrogen here, look what's going to happen to the electron pair. It's going to be slightly closer to carbon, but see how it's very in between. All right, so this is partially negative and this is partially positive, but the electron pair still is in between. Electron pair is still close to both of them, right? Close to each atom. So that's why we say it's not very polar. Not polar, I should put. Close to each other, to each element. So the bond has little polarity. This covalent bond has little. You could tell there is some, right? Little polarity. So we would call it a little polarity. Now let's look at carbon and fluorine. So we would call this not very polar. Not too polar. All right. Now let's go over here. Let's go over here. Can you add very? This oxygen-hydrogen bond is very polar, and I should have distinguished between that and this nitrogen one. All right. This is 0.9 difference, so this is considered polar. All right, because nitrogen's hogging, but it's not hogging as much as oxygen is, the electron pair. All right, so these highly electronegative elements like oxygen, fluorine, chlorine, etc., nitrogen are electron hogs. They hog the electron pair. Well, this difference we know, 2.5, but this guy is 4.0. So we have a partial negative charge here with the big guy with the 4 electronegativity. And then we have a partial positive sign on carbon. All right. So what would that mean if we actually had the bond? All right. it would mean this, that the electron pair is over by the fluorine. So this is very unequal sharing, isn't it? Very unequal sharing. If this was two kids playing with a toy, fluorine wouldn't be invited over again to play. So these highly electronegative atoms are like kids that don't share. All right? Very unequal sharing. So we would call this a very polar bond. So now we see what the electronegativity difference means. It means the electrons are not shared equally. So a significant electronegativity difference means the covalent bond is polar. And the electron pair is not shared equally. Remember, and I'm talking about these two guys that are in a covalent bond are not shared equally. All right. So I hope that you look at this and think, hey, this looks really cool. I really like this kind of technical thing where it, by simply doing this lowercase delta, lowercase d in the symbol fonts, it shows that a partial charge, and it reveals to us the location of this bond. These two electrons are much closer to the nucleus of fluorine than the nucleus of carbon. All right, in this one, carbon pulls a little harder. This electron pair is a little bit closer to the carbon nucleus than it is to the hydrogen nucleus. All right? And similarly over here, oxygen is such a hog that the electron pair is very close to the oxygen nucleus compared to the hydrogen nucleus. And so it really pulls on those electrons because of its high electronegativity value. All right, so when Linus Pauling made up this chart, you can see how amazing that was. So what I want you to do is to do the same thing with these. All right, so go ahead and do first hydrogen and sulfur. And we have these, let me make this big enough to have examples here. All right, just a little smaller. Okay. All right, I wanted you to be able to see the examples. So now do the same thing. Find the electronegativity of hydrogen and of sulfur. Decide who is partially positive and who the element is that's partially negative. Why don't you go ahead and do that with all of these first? All right. In this first one, didn't we have 2.5 and 2.1? All right. So which one's partially positive and which one's partially negative? You make the decision now and put the symbol. So I, in the meantime, will just draw the lowercase delta. All right. So the one with the highest electronegativity attracts the pair of negatively charged electrons more. So that gives it a negative sign because it's closer to the negative electron. All right, and so this one would be positive. All right, now let's go and do the chlorine-chlorine. All right, so figure out the electronegativity difference. Well, you're noticing it's the same element. This is a diatomic atom, isn't it? So regardless, 3.0, 3.0, there's no electronegativity difference, meaning this is not a polar bond. Whereas this guy is not very polar at 0.4 difference, but it's a little bit polar. So let's talk about what these two mean then. So let's draw hydrogen and sulfur, all right? And you put the electron pair, show where it would go. And do the same thing with chlorine and chlorine. Put the electron pair location based on what we've just figured out. So let me give you about 30 seconds to think through that and see what you come up with. Well, on HS, it's only a little bit polar and towards sulfur. So we probably would put the pair about like that. See how it's not very polar at all. There's almost equal sharing. Almost, but not quite equal sharing of that pair of electrons. Equal sharing of that pair of electrons. Oh, here it is. Well, if Cl2, Cl bonded to Cl, if there's no electronegativity difference and it's not a polar bond, then these are exactly between those two elements. All right, these guys share the electron pair equally. Does that make sense to you? All right, now go ahead and do the bond C-Cl and hydrogen-hydrogen. All right, go ahead and do those. Now, get started. 30 seconds for each one, beginning with the polarity. Excuse me, beginning with the electronegativity of each one. So you see why what Linus Pauling did was so important. All right. So we can see that one is going to be polar and one is not. All right. And so the difference in carbon and chlorine is about 0.5. All right. So it's kind of it has a small polarity, we would say, at 0.5. All right. And of course, it would show an unequal in that 2.5 and 3.0. This guy would be the negative one at 3.0. And this time carbon would be partially positive. All right, small polarity. And the bond would be closer then to chlorine, wouldn't it? Yeah. But not right on chlorine because this has small polarity. And then we saw that since this is a diatomic element, all right, molecule, the bond, the electron pair should be perfectly fixed between the two, right? Just like that. So, not a polar molecule, not a polar bond. All right. As technical as this is, I bet you now are going to be pretty good at it. So, the question is, what does the polarity of the elements in a bond show about the sharing of the pair of electrons? Which, is this little guy. We said this was the covalent bond. It's like I put peas in a pea pod, right? Go ahead and write that answer. What does the polarity of the elements show about the sharing? So, the greater the bond's polarity, dot, 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 that's your prompt. The smaller or no bond polarity means what? And remember that sharing the pair of electrons is what the question is about. So the greater the bond's polarity, tell me about the sharing of the pair of electrons. And the smaller, or if there's no bond polarity, tell me what that means about the sharing of the electron pair. So this is when I'm going to see whether you have comprehended or if you have followed along carefully with what we're talking about. All right? So my expectation is that you're smart, and you're smart enough to realize that if you just pay attention, I'm going to teach you something that's even fairly difficult. But my focus is always to teach it so you can understand it. All right, if you're not done right there, you can come back. I want to explain something here about the polarity of the water molecule, because don't we know that H2O, when we did the electron dots, we knew we had hydrogen, all right? So we had 1, 2, 3, 4, 5, 6, and we knew that oxygen needed 2 more. So there was going to be a hydrogen. All right. So there we have oxygen now. All right. When hydrogen gives its 1 electron, well, let's give that a little more substance. Let me make that bigger. Yeah. All right. So here we have, yeah. All right. Hydrogen's electrons. Now the question is, what can we tell about this molecule? Well, hydrogen 2.1 is the electronegativity, 3.5 of oxygen. So how polar is this bond? Well, look at the difference. We said oxygen-hydrogen bond was so polar, right, that the 3.5 electronegativity made oxygen partially negative, leaving hydrogen partially positive. And that means I'm going to erase this bond now. Whoops. Didn't mean to be. All right, and I'm going to put this bond very close to oxygen. And in fact, it might even be closer to that. And then similarly, all right, we have this hydrogen, all right, and the same thing applies. It's going to be partially positive, and this is going to be partially negative on the end of this bond. And so this bond is going to be very close to oxygen because of its high electronegativity. Therefore, all right, this is a highly polar bond, right? Highly polar. So water has 2 highly polar oxygen-hydrogens, highly polar oxygen-hydrogen covalent bonds. Now, does this ring a bell? Something we know about water and solubility? Do you remember I was drawing water something like this? Like this. And then I was doing these little partial positive, partial negatives, partial positives, partial negatives, partial positives. And we were saying that the water molecule right here, this guy attracts the positive sodium ion because it's negative. And these guys attract the negative chlorine ion from, all right, so to break down the salt crystal, to break down the sodium chloride crystal. Do you remember that now? And how I said I would explain that to you later? So when I do it like this, it looks kind of messy, doesn't it? But the same idea applies, that some sides of the water molecule are positive and some sides of the water molecule are negative. Oxygen side is going to be negative. Hydrogen sides are going to be positive. All right? So that's what gives water some of its unique polarities. So water, because it has 2 highly polar bonds, all right, and then I would say water is a polar molecule. It's made of 2 polar bonds, right? But it's a polar molecule. for a different reason, because the molecule is asymmetric. The bonds are asymmetric. And I'll show you what I mean by that again. So oxygen, and remember how these were not going different directions. They're not like this, are they? If these were arranged like that, this would not be a polar molecule, even though it had polar bonds. But because it's more like this, that's what asymmetrical bonds mean. They're not symmetrical. All right, so they create a polar molecule. All right, so water is a polar molecule because the bonds are asymmetric and pull more in one direction than the other. Now, to start cementing this information, all right, so these essential questions are now written here below. All right, and these last three, all right, this one, and this one are the ones that we have discussed primarily today. All right, so now I want you to go through and use the rest of the class period to answer these questions well. And I want technical responses that are based on the details from our lesson. I don't want you looking up on Google because Google won't use the words I used. It will describe it in a different way. If I don't recognize the way you're describing it, I'll think you're copying from Google. So you definitely don't want to do that. So let's just put do not copy from Google because I recognize it. And it's always going to be a little more general than what I told you specifically. Do not copy from Google. I recognize it immediately. It's more starched. I recognize it immediately when you do that. I want you to construct your own answer to prove your knowledge, not copy something. All right, you get it? I don't want you copying anything. I want you constructing an answer based on what you have learned in this lesson. All right. Now, so these lessons are now about the same size, and I want you to answer these. All right? So keep working on them. I wish you the very best. Go.